function, this is what we want to sketch. It's a cubic graph. So a cubic graph has generally that shape. That's what a cubic graph looks like.
Yeah.
So it should intercept, it can have up to 3x intercepts. So we're going to work that out later on, but that's sort of the general shape we want for our graph. So it's a cubic graph, it has a power of 3, so how many turning points do you reckon? 2? So that's what we're looking for, 2 turning points. So 2 turning points, what about points of inflection? 2 turning points, so 2 turning points means there's 2 types of concavity, so we should look for about 1 point of inflection. So, first part is find the stationary point. So every time we're looking for stationary point, we have to derive it. Everyone's happy with my derivative? No mistakes?
Not yet.
Not yet. Okay, so once we've derived it, do you remember, since we're looking for stationary points, our derivative has to be equal to 0. So f dash x, I've changed f dash x with 0. And now what I've created is, instead of a function, it's a quadratic equation. I'm going to solve this quadratic equation by, someone said something like 3.
I did. I said 3.
Yep, divide by 3. So dividing everything by 3, we have a quadratic equation that is x squared minus 2x minus 3. I reckon this is really easy to factorise. What would it be?
3.
X minus 3.
Yeah, x minus 3, x plus 1. Okay. So that means what are our x values?
3 and negative 1.
We solve for our x values, 3 and negative 1. Since we're looking for stationary points, and stationary points are sets of coordinates, we only have x value, so we're going to go find our y value. So when x equals 3, where would I substitute this into?
Original equation.
Original equation. So I want to substitute. So when x equals 3, y equals 3 cubed minus 3 times 3 squared minus 9 times 3 plus 1. Did anyone get that answer out? Nope. Okay, so 27 minus 27 minus 27 plus 6. Or plus 1.
So it's minus 26.
Minus 26. So our first set of coordinates is 3 minus 26. What would our second set of coordinates be?
1.
Yeah, so we're substituting x equals 1 into it.
X equals negative 1 is negative 1 is
1 cubed minus 3 times 1 squared minus 9 times 1 plus 1.
Is it x negative 1?
Sorry, negative 1. Negative 1. That will actually. So that's negative 1 minus 3 plus 9 plus 1. So would that be 6? So we have a turning point at negative 1 and 6. So that's our 2 turning points. We're going to determine the nature of these 2 turning points. You can either use the table of values or you can substitute it into the second derivative. So which route would you prefer? Table of values?
1.
Yeah.
Good.
Alright, table of values. So what we're going to do is x and first derivative, so should be consistent, f dash. So we'll test for the first one, which is 3. So I'm going to use the value less than 3. So 2 is pretty good. I'm going to use the value more than 3. So we'll use 2 and 4. 2 and 4 are good. They're good values to use because they don't coincide with that negative 1, so it doesn't overlap. Substituting 3 into the first derivative should give you 0. Substituting 2 into the first derivative, so the first derivative is what?
Minus 9.
Minus 9? We can test it. F dash 2, 3 times 2 squared minus 6 times 2 minus 9.
12 minus 12.
Minus 9.
That's okay. What is it?
Minus 9.
Minus 9. Okay, so it's minus 9, so it's falling, flat line. What at the fall?
15.
15. So positive 15?
Yeah.
Positive 15. So it's going up. So what turning point do we have?
Middle.
Middle. So what do you reckon the next one would be then?
Maximum.
Max, but we'll have to test it. -1. So a number less than -1, -2, and a number greater than -1, which is 0. Remember, we're substituting into the first derivative, not the original equation. That's 0. -2 into the first derivative would give you, what is it? 3, -2 squared minus 6. You guys are faster than me, you've got calculators.
15.
15 is it? Okay, so it's a positive, so it's going up. So that's a good sign. Because we're looking for a maximum turning point here, so it's going up, it flat lines. What at 0?
Minus 9.
Minus 9. So obviously it's going up, flat lines, and it goes down, so it makes a maximum turning point. So we've determined the stationary points of the two coordinates, set of coordinates. So now we're going to have to find the point of inflection. So remember, points of inflection occurs when you have a change in concavity, and that's already present. We already have a maximum and a minimum turning point. So our concavity has already changed. So now what we have to do is we just have to find what the point of inflection is. So go back to your first derivative and derive it again. Make sure you're deriving this one, not the simplified one. Okay, so original, not simplified. So the second derivative is going to be 6x minus 6. And because we're looking for point of inflection, we're going to substitute f double dash for 0. Because remember, second derivative equals 0 will help us solve for our point of inflection. So solving for x, we get positive 6. Therefore, x equals 1. We just need to check that the concavity does in fact change, even though we know that we have a maximum and minimum. We should always check. Okay, so we're checking for change in concavity by using second derivative. Even if you don't formally write it down, you can actually just check by just punching in some numbers on your calculator. So we're going to do 1, 2, and 0. Substituting 0 into this one, into the second derivative, you should get negative 6. And substituting 2, you get 2 times 6 is 12, 2 by 6, positive 6. So you have a negative and a positive, so concavity changes.
Doesn't sound like it.
So concavity changes. So therefore x equals 1 is a point of inflection. But not done just yet. So moving on to the other side, we still need to find the coordinates. These questions aren't given to you just like that. We break them up. So if I was to give you a curve sketching question in your exam, I'd break it up to find the turning points, find the point of inflection, find the x-intercepts, then sketch. So
How many marks is that question?
that would be Well, point of inflection, turning points itself would be 1 mark for deriving, and then 1 mark for solving. Usually it's a quadratic equation, so you have to have 1 mark for solving, and then probably 1 mark for each set of coordinates, so that's 4 marks for 2 stationary points. And then you get 2 marks for points of inflection. So far, that's already 6 marks, and we haven't finished the question yet. So these questions are supposed to be lengthy, but they're broken up.
So we could ask for minimum and maximum, we get marks there too?
Yeah, you probably would as well. So it would be like determine its nature. So once you've already found the coordinates, once you've determined its nature, you've applied a mathematical process, so that's also a mark. So we're up to now, what is it? 12th step. So our 12th step. In our 12th step, we want to find the coordinates of the point of inflection. So we're going to find the coordinates. We already know that x equals 1. So what we have to do now is we need to solve for y. So when x equals 1, y equals 2. So substituting it into the original. Just be careful that you're always substituting it into the original when you're solving for coordinates. What is it?
-10.
Negative 10. Okay, so our coordinates are 1, negative 10. And that's our point of inflection. It's not a horizontal one. It's just a point of inflection that occurs between 2 different turning points. And that one is actually in between 3 and -1, isn't it? Remember how I said sometimes it's midway between? 1 is midway between -1 and 3. Okay, so 13th line of working out is x and y intercepts. X and y intercepts now. Okay. In 2 unit, I'm not going to expect you to know what the x-intercepts of that function is. So we're going to ignore x-intercepts for the 2 unit class. 3 unit, you need to know how to do x-intercepts.
So do we have to know how to do y-intercepts or what?
Yeah, we're doing y-intercepts now. So we're going to ignore x-intercepts for now. And the reason why we're ignoring x-intercepts is because 2 unit students haven't been taught how to find the solve sort of cubic graphs or cubic equations.
Have 3 unit students been told that?
Yes, you have.
Oh, no.
Good thing I don't remember. Oh,
It's polys.
okay, that's why. Never mind.
Alright, so we're going to ignore x-intercepts right now. We're going to solve for y. We're going to just solve for the y. The y-intercept. So y-intercepts occur when x equals
0.
Yeah, when x equals 0. So substituting 0 into that function, substituting 0 into the function, what do you get? 0,
Plus 1.
0, sorry, the original, plus 1? So we have a y-intercept plus 1. Next step of working out was domain and range. Alright, looking at this function, the domain is all the possible x values. Is there any restrictions? No? No restrictions? So no restrictions is
Oh, really?
all real x.
What would be an example of restriction?
Huh? Well, usually restrictions occur usually when you have something that has a denominator where you can't make it equal to 0. So this one is x can't be equal to 1.
Yeah.
There's no, or anything inside a radical symbol or a surd symbol. Usually, remember your surds can't be negative for real solutions. So these have restrictions. And what about your y? So all real x, all real y. If I can substitute, boys, if I can substitute every x value, every value for x, I can yield every value for y. So our domain and range is all real x, all real y. Next part is asymptotes and limits. So you don't need
Just curiously, when's our test?
week 6. So week 6. You have a curve sketching question in your test.
Like it is on this one.
So for 3 unit, is there a revision book for that as well?
Yeah. It's coming.
Awesome.
Can you please not rub out 10 and 11?
No,
That's
I'm not going to rub that
necessary.
side out. I'm just going to rub out the middle. So where are we up to? 15th line of working out. We are going to ignore limits.
1500.
We're going to ignore limits and asymptotes because you have all real x's and all real y's, so there is no limits and asymptotes. There is no part of this graph where it's discontinuous. So the graph continues forever and ever. So let's just say this is what the graph looks like. It probably isn't, but say this is what a typical cubic graph looks like. Because it's all real x, this graph continues along the x-axis in both the positive and the negative direction. It continues down the y-axis in both the positive and the negative direction. So there is no limits to this graph. This graph continues forever and ever. So that's why there's no limits or asymptotes, so we can ignore that step. So the 16th line of working out is use symmetry. Do you remember odd and even functions? Alright, so just a quick refresher. An even function occurs when, if I substitute the negative of x into the function, it should equal the original function. And odd, this is even, odd occurs when I substitute a negative and it equals to the negative of the whole function.
This is
That's odd. So that one's even, that one's odd.
isn't this graph on
We'll see what this graph is. I think this graph is neither. You can also have neither. Neither makes you feel like we've wasted a lot of time doing it, but...
Great.
Huh?
Great.
Once again, if I'm asking you odd, even, or neither, I'm giving you marks for the process, so...
So it's not symmetrical.
Yeah, is it not symmetrical? Well, this is a rough graph. This isn't what the graph looks like. This is just an example of a cubic graph. But we're going to look at our own graph.
Excuse me.
Maybe
Mhm.
for line 13, should it be 0 minus 0 minus 0 plus 1? No.
Yeah. So our own graph is x cubed minus 3x squared minus 9x plus 1. Alright, so this is just the function as is. Let's substitute the negative of x in. Okay, so I'm substituting every value of x for negative x. And I get negative x cubed. Okay, minus 3x squared plus 9x plus 1. Now what I'm going to do is I'm going to have the original function, but I'm going to make it negative. So I'm going to times it to negative 1. This is our original. It's pretty much just changing all the signs. Does looking at our 3 different types of functions, does any of them match? Nope. So it's neither.
So is this still symmetry, miss?
Yes, it's still symmetry. So it's neither. This is important. This is revision, but
that means it's not symmetrical.
huh? So it's not symmetrical. So if it's neither, it's not symmetrical at all.
So then what happens if it's odd and even? What is
If it's even, it would be symmetrical about the x-axis, so it would look like a mirror image. So, see, sorry, the y-axis. See the y-axis? It's going to be a mirror image. So parabolas are symmetrical graphs.
So what happens if it's odd?
If it's odd, it means it's rotated 180 degrees. So we have part of the parabola, we rotate it 180 degrees. This is what it would look like.
Right. So it's like a point of inflection, basically.
Yeah, pretty much.
Okay.
So we don't have, so our graph is not symmetrical about the y-axis and it's not rotated 180 degrees. Now I think it's time, even though I said draw up a table of values, now it's time to actually sketch it.
Yay.
I know, it's long, but
I'm sorry, but sketching the graph wasn't on the recipe.
wasn't it? It was supposed to be sketching.
Yeah, you're doing an included ingredient here.
Using prop.
It's garnish.
It's not fun. That means it's optional. So
Just to make sure.
Alright, so we'll sketch it down. Okay, so we're not taking into consideration the x-intercepts because we don't know how to solve cubic equations. Yeah, bring it, people should know.
Yeah.
Sure.
Alright, so y-intercept was what? 1? What was our minimum turning point? I wrote to that, so you need to tell me.
Let me
0.
Yeah, I'll go.
X equals 3.
X equals
26.
3 minus 26. Okay,
Oh,
so
you're
our
right.
graph
God, it
is-
feels like years ago that was.
My graph doesn't feel big enough. Doesn't look good. Fun.
There we go. No, it doesn't line up. There we go. 3, so that's minimum? Okay, what about maximum?
-1, 6.
Minus 1, positive 6?
Yeah.
Okay, so that's max. And point of inflection?
1.
One.
One.
One
what?
1 and negative
1, negative 10. Okay, so we have a maximum turning point. So our graph goes and cuts through at 1. It should change concavity at 1, negative 10.
10. Ah, so
And it's, I'm going to try and join it up to 3 and negative 26. Not to scale, of course. We're going to curve it up. We don't know what that x-intercept
sure,
is.
right.
That's fine. I'm going to curve the graph downwards. That's what our graph looks like.